because you were in parallel with the inductor, and that was a high-pass circuit, and this wasn't a high frequency compared to that point. And so this is actually demonstrated. The reason this is bad on an exam is that if you really want to show that the resistor can't really get all of it, you have to keep all the digits 5,000.89 to show that the resistor's voltage isn't really 10. And so that's why this isn't a good exam problem. Closer to the crossover point is a good exam problem. But this is good for a review because it leads to understanding. Yes?
Regarding, like, when we're solving for the voltage, we want to, instead of writing everything with the phase and the magnitude, you want it to be separated for the exam?
I don't know what you mean by that. You mean a series of calculations that lead you to magnitude,
right,
and an independent series of calculations that lead you to phase?
Right.
Yeah, that's fine.
Okay.
Do them right, and you'll get all the credit.
Alright.
Okay. So, now, this was all the standard analysis, so what goodies do we have? If the voltage across the inductor is used to power another circuit, would this system be considered high or low pass? Across an inductor is high pass. If the voltage across the resistor is used to power another circuit, high or low pass? Low pass. Okay? You have become bored with this circuit. Oh. Okay, and I have become bored with this question. You have become bored with this circuit and decide to change it into a radio tuner designed to tune a frequency of 800 kilohertz. What circuit element would you add to make the new circuit? So, if you got an R and an L, but you want to make a tuner, what are you missing? Capacitor. And what is the resonance condition? That's the resonance condition. That omega L equals 1 over omega C, because that's how the inductor and the capacitor cancel each other, leaving the circuit acting like a pure resistor. Therefore, since I've got the L, the only unknown is so what C do I add? Oh, wait, I've made a mistake.
Wait, the frequency is what? 800.
Yeah, this is the frequency that the old circuit was driven at. The new circuit, it says run it at a frequency of 800,000. So in fact, I made a mistake. So what did I get for this capacitor? Really?
Yeah.
Yeah? Which is 13.2 10 to the minus 12, which is known as picofarads. And that's called the puff test. If you hear a puff, you fail. Okay? So that's what people say, you know, oh yeah, I wired my circuit and it passed the puff test. It means it didn't blow up. So that's good so far. If you fail the puff test, then you start over. Okay. So, everybody happy with that? Yes? Probably not. I'll discuss how it will be done, and you guys will say, so that's no big deal, huh? Okay. But I think a solid understanding of these circuits is what I really want. Yeah?
Can you explain what you mean by resonance condition?
Yes. Below this frequency, the capacitor wins. Above this frequency, the inductor wins. At this frequency, because the capacitor and the inductor battled it out and canceled each other out, the only one left standing is the resistor. So you can see that the capacitor and the inductor, mathematically, you can see them battle one another out. Plus I omega L minus I over omega C. This is a fight because one of them says, push the phase up. The other one says, push the phase down. And they fight each other. And if omega L is bigger than 1 over omega C, i.e. it's more ohms, the inductor wins. If 1 over omega C is bigger than omega L, the capacitor wins. And the resistor is just standing there on the sideline, watching them duke it out. And when omega L equals 1 over omega C, they both lose, and the resistor steps forward and says, well, I guess I get it all. And so it's that one frequency that matches this, that's called the resonance condition, because every other frequency does not come through. A little bit higher frequency, the inductor wins. A little bit lower frequency, the capacitor wins, so the resistor is just sitting there biding its time for a signal to come through with just the right frequency where those guys kill each other, and then the resistor says, I'm the last one standing.
So the high pass is just when the inductor wins and the low pass is when the capacitor wins?
No, because you see a resistor is leftovers. So when a resistor is with an inductor, the leftovers are low frequencies. When a resistor is with a capacitor, the leftovers are high frequencies. When the resistor is with an inductor and a capacitor, the only leftovers are last one standing, because they killed each other off. And so that kill each other off is the resonance condition for the circuit. Okay? Everybody follow? Yeah.
Inductor, takes all lines, doesn't matter what
Well, it takes most of the high frequencies. The higher, the bigger the percentage you get. So when you're way past omega L equals R, the inductor gets almost everything. When you're way below omega L equals R, then the resistor gets almost everything. And it's a smooth turnover of who gets it. You know, that goes from, at extremely low frequencies, it's all resistors. At extremely high frequencies, it's all on the inductor. And at the frequency where omega L equals R, it's 50-50. Because the inductor's voltage and the resistor's voltage will be the same. Okay? So, make sense? All right. Click. Oh, it's already clicked. Is that a hint? Now this one I changed some of the intermediate questions, but the last one for extra credit was actually on an exam. And I got a letter from a student's parents. I'll tell you about that. So anyhow, here we go. We've got an R, an L, and a C. And the first two steps, magnitude and phase of the impedance. So, it's in series and therefore,
Sum.
I'm going to add them up. A plus IB, DE to I5.
A plus IB.
A plus IB. There's for the resistor. There's for the inductor. There's for the capacitor. That's in A plus IV format, right? But we need to write from this a magnitude and the phase. So the magnitude of the total impedance is
R squared plus omega L minus 1 over omega C quantity squared.
R was what? How much?
600.
600 ohms. Now let's calculate omega L. 2 pi times the frequency. What's the frequency? 500 times 10 to the 6 times an L of what?
1.4 times 10 to the negative 6.
Okay. So what do I get? The plus and minus 10 to the 6s will cancel. How much?
3 pi.
3,267.
About 3,000 what?
267.
3267?
Yep.
Okay. And that's in ohms, of course. Oops. What I just wrote is wrong.
You have to do minus.
Yeah, I have
over
to
negative.
subtract off the other. So I need 1 over omega C. That's going to be 1 over 2 pi 500 times 10 to the 6 times the C of what? 3. So that's 3 puffs. Yes.
I have a question. When you write formulas and why do you use the
Because I have to, in order to make it look like A plus IB, you see I've got 2 things times I. I need to factor out the I to make this I times the quantity. Then I can recognize this is A and that's B. So since the I came in 2 places, I pulled it out to make that. So when I do my formulas for how to get various formats, and I say A squared plus B squared square root, A is R, and B is that entire quantity, for instance. I couldn't hear him. In here? No, I plug in the numbers and solve it first. You could expand it, but, no, I would accept this as a perfectly good format. You wouldn't have to expand the quantity in parentheses inside of the square root. This is fine as it is. And in fact, as it is, it's more informative, because it sort of shows you the resonance conditions staring you in the face by when this and that are the same size, they subtract to 0. So, actually, this is a prettier format than if you expanded it. At least it's prettier physically. Yes?
You want, you want the magnitude, we have to write the first one.
Oh. You mean, do you have to write how you got here?
No, the first one, we want the whole side.
Do you have to write this in order to get that, in order to get to here? No. You can just go to there. Okay, so I still haven't calculated this 1 over omega C. It's how much?
106.
106.1.
Well,